of 8, guys. Hope if that answer is what I think it is, I'm gonna love it. Okay. All right, you need to tell me the answer, Hope, because I'm gonna steal that joke. All right, we're talking about trig functions, guys. Okay. Yes. See, I love that attitude. Love this one. All right. Okay, guys, we're going to be talking about trig functions, and we're going to be talking about I'm sorry. Okay, I'm gonna come back to that. I'm sorry. Okay, let's take a pause, guys, for just a few seconds. Okay, because I need to write this down. Why is the right angle insecure? Okay, we're going to answer this. We're going to have a brain break, and we're going to answer Hope's question, Hope's joke, because it's super funny. Think about it, guys, and then we're going to come back. We're going to come back to it because it completely caught me off guard. I love it, though. I love it. All right, we're going to be talking about our 3 graphs, the sine graph, the cos graph, and the tan graph. All right, and we call these graphs that we've got drawn down here our mother graphs. Mother graph. Okay, and the reason we call them mother graphs is because every other graph is going to be some sort of variation to what has happened to this graph. So when they give us the graph of sine x, if they change sine x to 2 sine x, they have done something to this graph. They've done something to this graph. Okay. They've done something to the graph. Same with the cos graph. If they say cos x minus 1, they have done something to this graph. So we are going to try and figure out what is it that they've done to the mother graph. Okay, so when we change up the graph and move it upside down and left and right and whatever, we're going to try and figure out, what did you do? That is, today's question is, what did you do? What did you do to the mother graph? Okay, give me a thumbs up if you understand what I mean. Okay. Give me a thumbs up if you understand what I mean. Cool, I've got 2, 3, 4 thumbs up. I'm gonna rewind again, Asi, and we're gonna get there, okay? I'm going to explain again, and we're going to be looking at exactly what these graphs look like. Okay, you can take a screenshot of the graphs that we have on the screen at the moment. And because, okay, we're going to be looking at the exact same graphs, but we're going to be moving them. Okay. We're going to be moving them around. Okay, excellent. So we're going to start by actually drawing the mother graph of sine. Okay, so what I'm going to do, guys, and we're going to use these same points over and over and over again. We're going to use the points 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. We're going to use these points over and over and over again. Now, this is my x coordinates over here. These are my y coordinates over there. I'm going to call this 0 degrees, and it's also 0 for y. And then I'm going to put a point at 1, a point at -1, and then we're going to jump straight into it. 90 degrees, 180, 270, and 360. Now, everybody's going to pick up their calculators. Pick up your calculator, guys. We're going to get started now. Make sure that your calculator is in degrees. So the D at the top should be colored in, not the R, not the G, not any of that other funky stuff. Make sure there's a tiny little D at the very top that's colored in. Okay. So let's draw the mother graph of sine x. Okay. We're going to start by drawing the mother graph. Okay. we're going to go to our calculator and we're going to type in sine of, and we're going to replace x with 0. So go to your calculator, type in sine 0, give me an answer. Good. Sine of 0 gives us 0. So at sine of 0 degrees, my y value is also 0. Okay. Cool. That's 0 degrees done. Now go to sine of 90 degrees, guys. Sine of, oh gosh. I keep bumping into my finger and it's not fun at all. Okay, sine of 90 degrees is at 1. So we're going to go to where y is at 1 and where 90 degrees is, and we're going to meet. We're done with 90. You guys know where I'm going with this, yes? What's my next one? Sine of 180. Punch it into your calculator, give me an answer. 0, good. 0. Okay, then we're going to do the next one. We're done with 180. Go to the next one, guys. Sine of 270 will give us -1. So sine of 270 and -1 is there. And then the very last one, sine of 360. 0. Good stuff, everybody. Awesome. Now, I want us to do one more thing before we continue. I want you guys to go look for sine of 450 for me. Go punch in sine of 450 for me and tell me what you get. Good, we get 1. Good, we get 1. So does everybody agree? Just give me a thumbs up if you agree with me. If I go past 360, I'm repeating my graph again. Yes? If I go past 360, I'm going to start repeating the same thing again. So that's why we are stopping at 360. We're stopping at 360 because if I continue after 360, I'm going to be drawing the same graph again, which, why, when we already know we're going to get 1 and then 0 and then -1, then 0. 1, 0, -1, 0. 1, 0, -1, 0. So there's no need for us to go past 360 for this particular graph. Oh my goodness. The campus is going crazy today. All right, so we're going to draw, we're going to connect the dots. Remember to curve your graphs, guys. Function graphs are never straight unless it's a straight line graph. Every other graph is going to curve. All right, there we go. And this that we've drawn over here is the mother graph of sine. All right. Let's go to the mother graph of cos. Okay, we're going to do the exact same thing, guys. We're going to use the exact same points. 0 degrees, 90 degrees, 180, 270, and 360. Right, so we're going to start at 0 degrees, and I'm going to draw my y-axis over here at 1 and -1, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. And we know that if we go beyond 360, my graph is just going to repeat itself. So start with cos of 0, guys. Everybody's already ahead of the curve. Cos of 0 is 1. So my graph will start at 1. Funzo and Asbonge, you guys are cheating. I haven't even asked the question yet. I haven't even asked the question yet, and you guys are already done. I know, teacher knows. I know, right? Okay, then we go cos of 90. Cos of 90 will be 90. 0. Cos of 90 is 90. Cos of 90 is 0. So we'll draw the point here. What about cos of 180, guys? Cos of 180, -1. Good. And cos of 270, 0. And cos of 360, 1 again. Good, 1. All right, connect the dots, guys. Remember to curve your graph. Don't just draw it. Straight lines, it's not straight lines. We must curve our graph. And remember, Teacher Coco is not Pablo Picasso, and she can't draw to save her life. So you guys be kind. Be kind. Please be kind. Ne? There we go. Yes, absolutely. Thank you, Teacher Nels. I don't have to answer that question. Okay. All right. Awesome. And this that we're looking at here is the mother graph of cos. I know. I have to remind them, Tiana, I have to remind them not to judge me. Right. All right. Let's go to tan. Right. Let's go to tan of x. And we're going to do the same thing, guys. 0. But instead of 90, I want us to do 45 degrees, 90 degrees, 135, 180, 225, 270, 315, and 360. All right. It's a lot, I know, but we're going to do it either way, guys. We're going to do it either way. All right. Let's look at all of these points. Let's start with tan of 0, guys. Tan of 0. That's it, gift. Amazing. Tan of 0, guys. That's it, Ovayo. I was about to wonder, Ovayo, what is negative naught? Okay, good. It's 0. What about tan of 45? Tan of 45 is? Good, it's 1. It's 1. What about tan of 90? It says math error and it says undefined. And the reason why it's undefined, guys, let's think about this. If I had drawn, let me go all the way back up. Do you remember when we used to draw these things, guys? Do you remember when we used to draw these things on a Cartesian plane like this? And this was X, and this was Y. And you said that this was 0 degrees, 90 degrees, 180 degrees, 270 degrees, and this would take us back to 360. Do you guys see why my graph repeats after 360? Does this make sense? Give me a thumbs up if you can already see why my graph repeats after 360. What's going to happen, guys? I'm going to start at 0, go all the way around to 360, and then repeat again around, and again around, and again around. Askewele, come on. You know, it's because after 360, I'm just doing the same thing again and again and again. That's why. It's a revolution. Yes, that's it, Samuel. But now here's the problem, guys. Here is tan of 90. Here's tan of 90. Tan of 90 sits on this point, right? It sits on this point. And let's say, for instance, this is don't tell them. All right. Hope was about to give away the secret to the joke. No, don't tell them. Don't tell them, Hope. That's our brain break. Okay, cool. All right. Esona, I know how to play that game. Don't even. All right. So if we put 1 over 0, we're going to get undefined, guys. It's going to be undefined because we can't divide by 0. Same as if we came down here. The point down here would be 0, -1. At 270, my tan of theta would be equal to -1 over 0. -1 over 0 is going to give me undefined. So if we go back to our tan mother graph, at 90 degrees, we're going to have issues here. This we call an asymptote. Okay. But now let's continue, guys. Type into your calculators tan of 135. What are we going to get? Tan of 135? -1. Good. Where did I write 36? Oh, sorry. There. Okay. Okay. Yes, it's -1. So tan of 135 is at -1. What about tan of 180? Good. It's 0. Cool. Do the next one, guys. You know what's coming. Keep going. Tan of 225. Good. It's 1. And we already know tan of 270, undefined, it's going to give us a math error. So that also becomes an asymptote. Okay, good. Do tan of 315 for me. That gives us -1 again. And tan of 360, 0. There we go. Amazing, amazing. All right, let's put our graph together, guys. We're going to put our graph together. And again, I would like to reiterate that teacher did not go to teacher Coco didn't go to Pablo Picasso school. She doesn't know how to draw. Okay, so bear with me. Okay, so I even missed the mark. Oh my gosh, I missed the mark. Okay, let's try that again. There we go. All right. Remember, guys, we can't touch our asymptotes. Okay. We can't touch those points where our graph goes. We can get as close to them as possible, but we can't touch them. Right. Same as on this side. I can't touch this line here, but I can come up like that. And then on this side, again, I can get close to it, but not touch it and stop there. Hi, guys, I tried. Hi, Ayaz.
Ma'am, so
Yes.
so we can't touch the asymptote. So then we should just do it like that.
Yes. So it's not allowed to touch those graphs. Remember, it's almost like
So
the
must
same
we
as a
still
hyperbola.
move?
Remember, the same with the hyperbola. There are lines that we can't touch on the hyperbola. It's the same thing.
Oh, I see. Okay, thank you, ma'am.
All right. Patu, what's up, my sweetie?
Hello, ma'am.
I'm my sweetie. What's up?
Ma'am, I have I haven't asked that line that you drew there by the 360, like is it like not allowed to go up, like beyond the
it can go up, but what happens after 360? What happens after 360?
Oh, it starts again. The graph repeats.
It starts repeating again. So you can do it if you want, but you're just going to be drawing the same thing as you would at 0, correct?
Okay, thank you.
Cool. All right. I'm sorry, guys. I almost called Patu boy, and I didn't mean to. I'm sorry. I'm sorry, Chloe. I'm sorry. Okay. Apiwe says, ma'am, are there graphs for the ratio reciprocals? I like that teacher now said no. The correct answer is actually yes, but we do them, I don't even touch them in high school. We do them in university because they look weird, guys. They look weird. So the graph of cot looks something like this. That's what cot of theta, like cot of x is. It looks like that. So we don't touch it in high school at all, at all, at all. We don't do it. Okay, because they just, yeah, hey, it's not the one. So we don't do them in high school. Okay, so don't stress. All right. That's it, oh, I mean, it increases and decreases, but whether it's increasing or decreasing, it can't touch the asymptote when it gets there. Okay, Samuel says, high school or FET? FET is high school. Okay. Yes. Funzo says, ma'am, is the tan graph the only one that has an asymptote? Yes. Okay. The only difference is that with the mother graphs for cos and tan, right? We're never gonna, if we just use the mother graph, we're never gonna get a number bigger than 1. And we're never going to get a number smaller than -1. Okay, so we can try this with an experiment. We can do a quick experiment, guys. I want you guys to go onto your calculator and click shift cos of 2. Type in shift cos of 2. It should give you an angle. What angle do you get? Actually, it's not going to give you an angle, but tell me, shift cos of 2, what happens on your calculator? Yeah, it can't be. You're right. It can't be. It won't give you an answer. It gives you a math error because our graph is strictly between, our mother graph is strictly between 1 and -1. Okay, so the other graphs don't have an asymptote, but also the mother graph of sine and cos can only be between 1 and -1. They can't go any higher and they can't go any lower. Okay, so does that answer your question? Yes, Samuel. Yes. And you are currently in FET, Samuel. Okay. You are in FET at the moment. All right. Just give me a thumbs up. Are we all happy with our mother graphs? Everyone happy? Teacher Nels, I was just telling them that right before we started this lesson, I went to the bathroom and I slammed my finger in the door and I even broke a nail. Like my finger is in
I'm sorry.
In pain. Like, I mean, when you see me doing
But that's the most sensitive part of your body. Like, is it your left or your right hand?
left hand, thankfully, because I'm writing with this.
Thankfully, yeah.
So, yeah.
Jeez.
So hey, every now and then, if you guys see me just doing this, it's because I'm hoo-hooing my finger. I'm doing a hoo-hoo with my finger.
Cold.
Right. All right.
Sorry.
Okay. Now let's do some things, guys. Let's do a couple of things to our mother graphs. Right. We're going to start with the sine graph, guys. We're going to go y is equal to 2. Sine of, I know this says theta, but we can replace theta with x. You can even replace x with theta. It won't make a difference. Theta and x just mean the angle. Okay, so we're going to go back to the mother graph of sine. And instead of writing sine of x in our calculator, we're going to go 2 sine of all our values. All right, so punch in 2 sine of 0. Guys, 2 sine 0. Okay, we still get 0. Cool. Cool, we still get 0. What about 2 sine of 90? 2, good. 2 sine 180. All right, so we're going to get 0 again, and then 2 sine of 270. Good, -2 will be there. And 2 sine of 360, 0. All right. So my next question, guys, is what did this 2 in front of the sine x, what did it do to my graph? What did it do to my graph, to my mother graph? Good, Namisile, that's exactly what I was looking for. It increased, good, or it kind of stretched it. It did this. It stretched it out, like made it like, right, made it taller on each side. It increased it. Where my graph used to go from 0 to 1, now my graph goes from 0 to 2. Okay, amazing stuff. Well done, guys. So just like Namisile said, this number here in front tells us about the amplitude. Okay, it's the amplitude. The amplitude of our mother graph is always equal to 1. That's why it just says sine x. It's the same as 1 sine x. But if we put a number in front of sine x, then this changes the amplitude. Okay, just like physics. And I'll tell you now, Gift, when you get to university, maths and physics, same WhatsApp group. If you take physics, you have to take maths. When you take maths, you have to take physics. Rule of thumb. Isn't it like that at your school? Yes. At school, you can't take physics without maths core. That's why. That's why. Because they're interconnected. All right. So we've just figured out that the number right in front of this changes the amplitude. It takes my graph where it normally goes from 0 to 1. Now it goes from 0 to 2. Apiwe says, ma'am, do we also calculate for the x and y intercepts with these graphs? Yes, we do. But you've already given them to me, Apiwe. Okay, you've given them to me. My x-intercepts are everywhere where we cut the graph at 0. There are my x-intercepts. There they are, at 0 degrees, at 180, and at 360. That's my x-intercepts, because that's everywhere where y is equal to 0. All right, does that make sense? We're going to talk about it a little bit more when we talk about interpreting graphs, which is next week. But yes, basically, okay, basically that's it. Those are your x-intercepts. All right, cool. Now let's add something else, guys. Let's add something else. I want us to look at the graph of sine of 3x. Now, what I want you to do on your calculators, guys, is I want you to go and type in sine of 3 times 0. So sine of 3 times 0, close bracket, like close bracket. Sine of 3 times 0 gives us 0. Cool, 0. Okay. Then instead of giving me sine of 90 next, I want you I love it. You guys are the best. Close brackets. Yeah. Okay. I want you guys to go and tell me what sine of 3 times 30 degrees is. 30 degrees. Go punch into your calculator, sine of 3 times 30 degrees, close bracket. Good. It gives us 1. Cool. I had to, you dared me, I had to. Okay, go into your calculator, type in sine of 3 times 60 degrees. Gives us 0, cool. Type in sine of 3 times 90 degrees. 3 times 90 degrees is -1. Cool. Type in sine of 3 times 120 degrees. 0. Cool. Sine of 3 times 150. One. Cool. We're back at 1 again. Okay. Sine of 3 times 180. We're back at 0. Okay. Awesome. Now I'm going to draw this graph very quickly. Thank you, Teacher Nels. Thank you for that. Cool. Guys, it's a graph. It's something. I drew something. Okay. Now, I have to ask you guys. I'm even lying. Look, I don't even need this part. We should have stopped at 120. I should have stopped at 120. I should have stopped here. Okay. Do we notice? No, bring back that other graph. Okay. Do we notice that we've finished one full graph in 120? Yes or no? Yes? We've gone from 0, come all the way around, and we finished the graph in 180. Yes? Okay. Now, I'm going to ask you guys, if we had to keep going, how many graphs are we going to be able to fit? Yeah, Teacher Coco. How many graphs are we going to be able to fit in 360? How many graphs are we going to be able to fit in? 3. Good. Isn't it? Yes, good. Isn't it funny that there's a 3 in front of this X over here? And this tells us how many graphs fit into 360 degrees, right? So if we want to know what the period is, if we want to know what the period of our graph is, remember guys, the period of the mother graph, how long does it take the mother graph to draw? One full graph is 360. Yes, that's it. So this point here in the front will tell us that the period is how long does it take us to get from the starting point and make one full wave? The way we would do that is we would take 360 and we would divide it by this number here in front, by 3. So how long did it take us to make one full graph? It took us 120 degrees. All right. Thumbs up if this makes sense. Yes, Tiana.
Ma'am,
Yes.
so if it was a 5 or 4, 6, was it also gonna be like 6 graphs in there?
Yes, absolutely. Yes. And you would find out, how would you find out how long it takes to do the graph? You would take 360 and divide it by 4, which means you would make a full graph in 90 degrees. So your graph would fit in this space here. You'd be able to do this like that in 90. And then you do another one in 90 and another one in 90. Okay, does that make sense? I hope that makes sense. Okay, so the period, or this number here in front of the period, tells us how long it takes us to go up and then down. It takes us 120. All right. Cool. Let us do one more thing. One more thing. Because we see now what has happened to our mother graph. Here's the next graph that we're going to do, guys. Sine of x plus 1. Okay, so go into your calculator, guys. Go into your calculator. Type in sine of 0, close brackets, plus 1. What does it give us? 1. Good, it gives us 1. Good. And then go into your calculator, sine of 90, close bracket, plus 1. 2. Good. Cool beans. Right. Then go to sine of 180, close brackets, plus 1 is 1. Right. Sine of 270, close brackets, plus 1. 0. Cool. And then sine of 360, close bracket, plus 1 is 1. Good. So tell me, guys, what did this extra plus 1 do to my mother graph? What did it do to my mother graph? It's definitely not drawn to scale, I'll tell you that. Good. It moved the graph up. It moved the graph up by 1. Just like Q. Remember Q in all those other graphs that we do? It's like the Y movement. It's the vertical shift of our graph. This number here in the front is a vertical shift. All right. Now, everything I've done over here, guys, I can do with my cos mother graph. I can do it with my tan mother graph. All of them will kind of sort of look the same. In terms of the movement, I know. Chloe, please don't be this person right now. There we go. I touched it. Yes. So let me ask you a question, guys. Apiwa says, so 1 tells us how many times the graph moved. Yes. So if this was plus 2, if this was plus 2, how many units up or how many units would my graph move? 2 in what direction? Up or down? Good. It would move up. If this number was -3, what would happen? What would happen to my graph? It would move. Good. It would move 3 down. Okay. You have to just like down, ma'am, up with these emojis. Love it. Good. It would move 3 units down. All right. I hope all of this makes sense. Give me a thumbs up if you understood everything that we've done today. Okay. If not, I don't want to leave you behind because we're going to do a quick summary of everything we've just learned. Okay. Yes, Namisile, we're definitely going to look at the tan graph. Okay, I'm not going to leave you guys there. The cos and the sine and the cos graph are the easy ones. It's the tan graph that starts getting, okay, it starts getting funky. All right, now I'm going to scroll back up and we're going to have a bit of a conversation. All right, so here are our mother graphs. I've given you guys the mother graphs already, right? We're going to start with sine, right? So the mother graph of sine is normally 1 sine x, right? If I put a number, that's okay, Sihle, that's okay. If I put a number in front here, let's just call this f of x is equal to a sine x. What will my a do to my graph? If I put a number in front of a, what will it do to my graph? It will stretch or it will squash my graph. Right, it will either increase the amplitude or decrease the amplitude. If it's a positive number, oh, that's what I forgot. No wonder we still have so much time. That's what I forgot. I forgot the negative graph. We'll have to go back and get it and do it. All right, it will stretch my graph. So it will change the amplitude. Amp, right. If I put a number here, if I put a number in front of B or in front of my X, what will it do? Yes, there are about 4 or 5 marks. Okay, about 4 or 5 marks. If I put this B here in front of my X, what will that change, guys? What will it change? Good. Tiana, what will it change? No, don't go away, come back.
Ma'am,
Good. It will change the...
period.
Excellent. And what does that tell us about how many graphs we can draw?
It will tell us by the number of the B, it will like tell us how much graphs we can do before 360. Am I right?
That's it. Ha! Mwah! I would literally give you a high five and a sweet if we were in the same room. Love it. Yes. It will tell us how many graphs can we finish in 360. Beautifully done. Well done. What happens if I add a number at the end? What will this Q over here do to my graph? What will this thing over here do to my graph, guys? Good. Namisile, it will move my graph where? It will not increase by Q, guys. It will move my graph either up or down. It will depend on whether Q is positive or negative. That's it, Asbonge. It will either move my graph up or down, right? So this is a vertical shift. Okay, I want us to do one more thing. One more thing before we continue, right? I need to give you guys one more graph before we continue, all right? Okay, we know that this is the mother graph. I'm going to keep the original graph only, just so like this thing doesn't get too cluttered. Okay. Ah, don't stress, gift is not that deep, I promise. Okay. Look at what I did now. Where's that other graph that was here at the bottom? Let me not erase that either. Oh, teacher Nels, I'm doing a great job, a wonderful job. Okay, there we go. All right, here's what I'm going to do next, guys. I'm going to add a negative here. Let's start at 0, guys. Punch it into your calculator. Negative sign of 0. Negative sign of 0. Paper 2. I start. So please give me some slack. Cut me some slack. Good. 0. Negative sign of 90. Negative sign of 90 is -1. Good. What about negative sign of 180? Good, will give us 0. Negative sign of 270. I know. 1, good. Negative sign of 360. Cool beans. Excellent. So what did this negative in front of my graph do, guys? Good. It flipped the graph. It flipped it. Yeah. Right. Now it looks like an infinity sign. Okay. I know. Good. It mirrored it. Good. So if this number over here changes the amplitude, if this number happens to be negative, it will flip my graph. Okay, or mirror it. Yes, Apiwe, it will flip my graph as well. Okay, now remember guys, all of this is the same for our cos graph. Exactly the same. Right, well, what's wrong with this thing now? Okay. F of x is equal to, right, same thing will happen with my cos graph, guys. If I put a number here in front of my cos graph, what will that A do to my graph? What will the A do to my graph over here? Last few minutes, guys. No, it will do the exact same thing. Yes, what will it do to my graph?
It will tell you how much waves. It will tell you if it increased.
Good. But what increased?
The amplitude.
Good. The amplitude. Good. It's the change in amplitude. Excellent. Change in amp. What if I add a number over here? Ayaz, don't go away. Come back. Where are you going? Come back. All right. What happens if we add a number over here? What does this number do, guys? Good. It changes the period. Good. Changes the period. Okay. And what happens if I add a number at the end? What does the number at the end do? What does this one do? Yes, Timolocho, that's it. It moves my graph up or down, my vertical shift. Right. All right, okay. Now, I want you guys to note when we come to the tan graph, right? Do you guys notice how my graph keeps going? It's just going to keep going up and down, right? Keeps going on forever and ever and ever. Yeah, it goes to infinity. So if I asked you guys, what is the amplitude of my tan graph? What is the amplitude? Remember, the amplitude in the graph means the point where it is the maximum and the point where it's the minimum. Okay, my graph doesn't have one. Okay, so our tan graph has no amplitude. No amplitude at all. No amplitude. Okay. It doesn't have an amplitude. That is why Teacher Coco strategically asked you guys to go find these points. I asked you to go and find 45 and 135 and 225, because there's no part in our graph where it turns. And I know that at 90, there's an asymptote. So that won't be able to help us. Okay. Lindo Gutre is also saying, ma'am, how do you find the range in a tan graph? The range of a tan graph is y is an element of all real numbers, all of them, because it goes to infinity and to negative infinity, all of them. Okay, that is the range of a tan graph. Cos has a low frequency. It's like a ooh, love it. Okay, cool. So our tan graph, guys, has no amplitude at all, but it does have a period. Let's talk about the period of this graph. We've got 1 minute left and JC is on standby. I see that he's here. Right. How long does it take us to finish one full graph of tan, guys? How long does it take us to finish a full graph of tan? Look for the full graph. It's going to be between 90 and 270. How long did it take us to finish that graph? 180. Part 2, be careful. This one is only half a graph. This part over here is only half a graph. So we'd have to take this one and put it together with this one to finish a full graph. So the period of a tan graph is 180. That's okay, my sweetie. It's okay. I used to make that mistake too. The period of a tan graph is 180. All right.